It's my pleasure to introduce Erik Willett from Functional Products. Dr. Erik Willett. I think I misspelled your name on the earlier slide.
It's not that we're absent in all of our stuff.
I've seen some of his other talks and they've been very energetic, interesting. So really appreciate you coming to campus to do this for us. So go ahead.
Thank you, Dr. Jackson. So I'm Erik Willett. I'm representing Functional Products today, and I'm talking about pop culture tribology. So this is something that, a big part of the round robin discussion was how do we reach younger folk, get them interested at earlier ages, and just a trend across all industries is attention span is become really a commodity. It's a resource. So I'm what you'd probably describe as a early career person. Been out of school for about 7 years. So working at Functional Products, essentially my first job out of grad school. I'll talk a little bit about my career, and then we'll look into different areas of extreme tribology and lubrication as they apply to pop culture phenomenon, popular things in the media, because you want to create a direct connection, trigger kind of emotional responses between something that somebody was really into and potentially science. So some science typically has a very kind of stagnant, very methodical approach to it. And if you want to reach into and kind of really pull at people's heartstrings, you want to make those attachments. The things they like are related to the things that we're also interested in. So Functional Products, we're a small additive company out of Ohio. So just the background of where I'm from and how that's going to color my perspective on things. So we do a lot of specialty lubricant additives. If you're buying small quantities for a lubrication project, we will cook up packages, additive chemistries. We do a lot of odd jobs, and we use polymer technology. So polymers have a lot of positives and negatives, places where they work best, but we utilize the strengths of polymers and their unique properties to solve problems in lubrication. That's kind of that 10,000 foot level beyond what we do. So we're sort of a bespoke additive company. We've been growing a lot during COVID, where a lot of the larger additive companies are kind of stumbling with things like SAP transitions, just these massive overheads they have in kind of tumultuous times. Well, we've been able to pick up a lot of that and support people because we're very quick on our feet, very dynamic. So my career, when you go to a conference like ILMA and you have some networking discussions, one of the big questions is how did you get into this? Auburn, as we've established, is the only tribology minor, the only place where you can really go and study tribology and have a reason for being a lubricants. A lot of people end up in this industry from family businesses, from just happenstance. They have an interest in material science, and then it kind of brings them in. One day they're working at a lubricant company. My background is chemistry, bachelor's in chemistry out of the University of Connecticut, with a focus in polymer science, so not even a minor, just a few extra classes. I really had an interest in polymers even before, so I've taken that through everywhere I've gone. Used to research biodegradable plastics, how to make them more simple to overcome some of the problems with biodegradable plastics. They melt too easy, you can't make a coffee cup. So I was making some modifications there. I did a lot of research experience for undergraduates, RU programs. I can't recommend those enough. I did I did 2 of them, one at UMass for gold nanoparticle detectors. So cysteine functionalized gold nanoparticles to detect milk poison. People are doping milk, and it was causing a lot of incidences out in Asia. And then I've also done things like fuel cell research and so on. So that's just, when you're starting out in undergrad, you might have an idea of what you want to do. By the time you've gone through 4 or 5 years, your outlooks, your perspectives are going to be completely different. Doctorate in polymer science at the University of Akron. So what drew me to Akron was just the polymer science program. Really, that's essentially the hotbed of polymer research. It's the Polymer Valley. So for me, having a program associated with my personal interests, polymers and everything they can do, really drove me to Akron above all else. I got involved with a lot of tech scouting, a lot of extracurriculars, clandestine extracurriculars, where conflicted with some of my advisor's priorities, and I was able to kind of make everything fit. So kind of had, like many people, a zigzag path. Functional picked me up in 2016. I didn't technically graduate until 2018, and they were pretty good support for kind of straddling industry and trying to finish up my PhD. And I've kind of gone from being a lab person to technical director to VP of research and development to now president. So there's a good joke I'm going to steal is, what's the difference between an introverted technical person and an extroverted technical person? The extroverted technical person stares at the other person's shoes when they're talking to them. And that's kind of where I've been. I have a bit of a flair for the dramatic, a little, I'm still kind of an introverted at heart, technical person, but how do we help more people? How do we grow our business? So that's what I've been interested in. So flair for the dramatic. So I also have a big interest in films. Pretty big part of my family is film, car culture, and things. We've got a lot of hobbies. So I'm going to talk about tropes. Tropes are used in movies and media. They're cliches, but they're also shorthand. So this is kind of your cultural touchstones I'm going to talk about today. Things that we see in movies as far as fast cars. We're going to talk about metalworking fluids and biotribology in movies, some video games, TV shows. All of that has some grounding in truth, and it's those tropes that give us kind of a shorthand where we don't have to explain everything to everybody every time when they watch a new movie. We use the tropes, our cliches that writers build in. A lot of those tropes have basis in lubrication and tribology. Let's talk about STEM. STEM, as far as attracting people to majors, we've got these great blockbuster, major motion picture movies like Oppenheimer's got the nuclear physics going on. Hidden Figures was a great work about the math behind the spaceship launches. Interstellar, playing with astrophysics and computers. But where's our tribology movie? When Dr. Jackson gets a biopic, and sometime in the future, potentially that could be our movie that gets people excited. But tribology is everywhere. Yeah, tribology is part of a lot of stunts. Like here's Jackie Chan sliding down a building, and then in some of the animated pictures, you have like the new relaunch of Spider-Man, Into the Spider-Verse. A lot of that biomimicry that allows Spider-Man to walk on walls. And then you have your classic stick slip phenomenon, like I was talking about, your moody cello music and things featured in shows like Wednesday. So tribology is, when you're creating a piece of media, part of our everyday experience. And if you are able to successfully incorporate our expectations for tribology, how things move, they slide, you have something that's a bit, that just reaches out and grabs people a bit more. So I'm going to talk about, I picked 3 things to talk about today that relative in the COVID era were pretty big hits for people. So things that could bring in an audience of people who are not really familiar with tribology, but how do we get them interested? What is tribology? How does it affect the things that they like or think are interesting? So Fast and the Furious, we're going to talk about Cyberpunk and this kind of new IP that's out there, this new sci-fi genre. And then we'll talk a bit about forged in fire and metalworking fluids, specifically quench oils. Okay, so Fast and Furious. Me growing up, I did a lot of work on cars, which kind of created this whole trajectory that kind of really drove me to lubrication. I really liked, taking cars apart. Drove a manual Ford Bronco 2, took the whole thing apart, put it back together again. And that experience has always stuck with me. So the premise is, fast cars, human and machine working together to get high thrills, high speeds. And it's really a very American phenomenon, is this whole car culture. Muscle cars, as back as American Graffiti. Fast and the Furious is a great example, one of the biggest movie franchises. And then recent pictures like Ford versus Ferrari, where we even have an international clash of Ferrari Corporation and Ford, so US versus Italy. But what you see is people don't change their oil. They might be working on tires, it might open an engine bay, but nobody's really changing the lubricant. What I'm going to focus on is transmission oils. As a kind of a more boutique type of additive company, we work with a lot of racers, independent racing organizations, small blenders that make a premium racing oil. One of the biggest consumers of this is the gearboxes, your manual transmissions and your differentials. Not going to talk about engine oil because it's about half the lubricant market, and I think it gets enough prep as it is. But we're going to talk about torque and how we're trying to avoid tearing our cars apart. I'm going to talk a lot about manual transmission oils, a little bit of ATF and how ATF is going to feed into EV lubrication. But essentially what I'm going to establish is if you go to the auto store and you look at all these different oils, this is going to be a kind of a brief primer and what's the difference between like a GL4 and a GL5 and all these different fluids you can put into the drivetrain. Okay, so the API GL system is a bit obsolete, but I think it's a good framework. I like cheat sheets and tables like this. So not a lot of people are using this GL system anymore, but I quite like it. It helps you kind of set some expectations for performance. So GL1 is something like an R&O oil, a rust preventative oil, maybe a light duty bearing oil. Up to a GL3 is probably going to be some of your industrial lubricants, way oils, hydraulics. And as we keep going up in GL number, we're going to have more and more EP load carrying properties. GL4 is where we start to get to the fast cars area. This is where we're using slightly active sulfur, some inactive sulfur, sulfurized fats, polysulfides and things, but definitely passivated. GL5 is where we're going to have the severe duty automotive gear oils. These are going to be your hypoid differentials, so really high torque for fast takeoff. And then these are going to use the most severe aggressive sulfur species that you can. Some cases like worm gear, where it's a yellow metal that can be easily attacked by sulfur, you're going to want sulfur free. So if a customer comes in, they want something designed to a certain GL level or application, this is a good primer. And then MT1 is going to be less passenger car, but more your big buses, public transportation type vehicles. And it's essentially going to be this heavy duty GL5 performance, but you're going to have to do it with a very mild GL4 type of chemistry. So big treat rates to make up for that. And we supply different packages that meet all these different levels. We also work with EP weld loads. So there's a lot more to life in tribology than 4-ball welds, but this is also a good framework for kind of what tier are we looking at. Then we build out with Phalix CP, FCGs and things, but this is just a good conversation starter. We're typically offering a GL4 at a 250 to 315 kgf weld load, and then your GL5s are typically at a 400 kgf weld load. We've built some things for some real custom racers up to 620, 800 or 800 plus weld loads for just stock car or for dragsters, because you don't want the gearbox, the differential that's transmitting the power of the engine to the tires to be torn apart. So drivetrain, there's a lot of different types of gears involved. In a manual transmission, you have a bunch of straight cut gears. That's going to be converting your RPM from the engine to torque. So as you convert RPM to torque, your power curve allows you to move the car faster. Your differential is going to break up that torque and allow the tires to rotate at different speeds. If you don't have a differential, it's very hard to turn your car if your back tires are forced to be parallel. So depending on the design of your transmission and the design of your differential, they might take the same oil or they might not. Manual transmissions in racing cars, this is a Muncie 4-speed. Manual transmissions typically are using yellow metal a lot. In order to make smoother shifting when a manual transmission, there are these brass rings that sort of float between the gears, and these help you to seat when you're shifting manually much easier. So you don't want that aggressive GL5 sulfur species in there. You're going to go with the GL4 in a manual transmission, unless it doesn't have these synchronizing or synchromesh rings. In a differential, it's going to be that spider gear set, mostly stainless steel. There you're going to be using that GL4, or up to a GL5 type of chemistry. So that's a big thing, is some people think they can take a GL5, but that's that aggressive sulfur, high EP load carrying property from the differential, and put it into the manual transmission, and you're going to have a bad time. It's going to eat through that copper. So a lot of it is, for the mechanical engineers, you have to, if you're designing, the lubrication engineer and the mechanical engineer have to work in sync. You have to know what's going to be in the bill of materials for the lube. You have to know what's going to be in the bill of materials for the gearbox. And then GL4, GL5. So kind of a summary. GL4 is going to be probably used in most of your passenger cars, your sedans, your economy vehicles. These GL4 is kind of rated for a spiral bevel gear set in your differential. So that's going to be a bit more compact, so it fits better into a sedan. A GL5 is going to be in your really high torque differentials in the back of the vehicle. You're going to see a hypoid gear set more in an SUV or a higher ride, because that hypoid gear set, where it's offset, takes up more space. So there's very simple, just going to the store, if you're an engine builder or a drivetrain builder, picking up a bottle of oil. If you pick up the wrong one, you could really fry your mechanical parts. And then MT1 is just a manual transmission, but it's built to that high performance GL5 spec. Automatic transmission fluids are a kind of a different animal altogether. So there's a lot of confusion. You build them completely differently. They're more like almost like a motor oil. You've got things like a wet clutch. So when you're shifting in the automatic transmission or shifting by itself, you have to disengage the clutch. The clutch is made out of paper, fiber, and ceramic, essentially kind of like sandpaper and metal sandwich. And you have to make sure that your fluid meets this proper friction and slip parameters, where your clutch is not going to engage properly. So ATF is almost like, compared to manual transmission formulating, is almost like brain surgery, I would say. It's very intricate, and you could see just the amount of small channels in the valves that drive an ATF system. And it's something like this valve train right here, this valve body on the right here, is going to be on the bottom of the transmission, and it's going to be actuating all of your gears. I could tell you everything that's in and here's where we start to get into some of the business end of formulating, is I could probably tell you everything that's in a manual transmission oil. But an ATF is really a packaged deal where there's a lot of chemistry involved. Over time, to keep up with fuel economy and CAFE regulations, where you're dinged or you're actually charged as an auto manufacturer if you don't meet this rising tide of fuel efficiencies. The trend has been lower viscosity fluids, higher speeds, higher efficiency. But what that's done is create, in combination with that wet clutch, that really complex testing that goes involved with it. What happens is ADCOs, big ADCOs, tend to package a lot of things together. So it's a bit more of a black box when if you're an ATF blender, you're typically taking the package that the ADCO gives you, and then you're blending that in at 10 or 15%. So it's something that is above kind of our scale to provide ATF, because it's so dialed into that, the clutch testing, all the complexities of that. But what I can say is, over time, what started out with Dex3 is sort of an engine oil spec, higher viscosities, almost like an engine oil. It needs the dispersancy to dissipate all, to survive the heat that a clutch throws out. Over time, as they get to lower viscosities and the margin of error for things like shear stability or mechanical wearing of the viscosity, it's become a hydraulic fluid with the Mercons, and then with the new Dex 6 and the Mercon ultra low viscosities, it's become almost like a gear oil. So you see this trend in a lot of fluids, even with the engine oils, as we're going to lower and lower viscosities over time. And then the future of automotive. So I think, EV lubrication, as mysterious as it might seem, I think follows this ATF trend where it's just more aggressive environments, lower operating viscosities for the fluid, and just tighter and tighter tolerances on the machining. So expect with the SAE, the J3200 specification that's in development, expect 15,000 RPM in an electric motor that's going to replace your ATF. It's your automatic transmission. It's going to be operating 150 degrees Fahrenheit, so extreme heat and extreme speeds. And we don't quite know what the nature of the lubricant will be. Like I said, ATF has evolved over time from a motor oil to a hydraulic fluid to a gear oil. I think EV fluid is going to look more like a base oil almost, with just additives. But it may end up being something more like a coolant as we have to dissipate all the heat of the electric vehicles. Okay, so we're going to dip in now to some biotribology. So this is really outside the area of, I'm not a biotribologist. I think this is a great opportunity for the tribology minor, is getting the biomed people involved because they're highly competitive. So where you've got, mechanical engineers just looking to get a job, you've got these pre-meds and such really looking to distinguish themselves. So I think that could be a big opportunity for the future of the industry. So Cyberpunk kind of is just, you can think of the Matrix, but instead of, connecting to the internet and all of that, it's more centered around biotechnology. So this has been a big Netflix show during the COVID era, pretty popular. There's some games and some movies and things. But it really revolves around prosthetics or cybernetics. And the premise of kind of the TV show is you can go in and it's almost like a tattoo parlor and get augmentations or prosthetics and things, and now you've got superhuman strength and things. Why I highlight this is to call out certain things and certain tropes in this type of sci-fi arena, is that with shows like this where you've got high-tech materials and things, there's a lot of hand waving. So my background is really material science, that whole polymer background. So people just say, oh, it's a polymer, it's an alloy, it's a ceramic, and that's what makes it work. So spy movies, science fiction, things like Blade Runner and the Cyberpunk show. And I think that, there's still some hurdles in that application. You have to, when you're a material scientist, you have to figure out there's always limitations, and not just by virtue of something being a polymer or an alloy, it doesn't make it, high performance or special. It's really about the material and the application selection. So you've got different materials and different challenges. So in the prosthetic hip and joint replacements, you've got really three areas. You've got polymers, traditionally ultra high molecular polyethylene, metals like titanium and titanium alloys or surface treated titaniums, and then ceramics, things like hydroxyapatite that can kind of mimic the natural structure of bone or bone marrow, and you can implant cells and things into. What's important to note about these three whole regimes of materials is that they do have different roughnesses or tolerances that you can machine them to. So polymers are typically cheaper or easier to manipulate because they're softer, but your roughness is going to be on the 1 to 10 micron level. So you're going to be probably operating in boundary lubrication conditions. So that's a pretty aggressive environment for a soft material. You can have a lot of wear, even though you've got this really slippery, cohesive polymer system. It can break down, form a lot of wear particles, and cause issues. So there's problems with the magic polymer that some of these sci-fi shows use. Alloys also alloys also aren't perfect. They could be machined to tighter tolerances. So we're operating now in that 1 to 3 lambda, the mixed lubrication, getting to lower friction. But you have problems with biocompatibility. Titanium might be compounded with things like chromium, molybdenum, and you don't want things like those heavy metals to leach out. So there's problems with these magic alloys that certain shows profess are the answer to everything. And ceramics could be even polished down to an order of magnitude finer, so 10 to the -3 microns. And you're talking, elastohydynamic. The EHL, elastohydrodynamic lubrication regime. So very low friction, but you have problems with now a very tough, rigid ceramic that doesn't quite mesh with the the modulus or the toughness of the surrounding tissues. So even though something's a composite or an alloy, doesn't make it special. It doesn't really overcome the vulnerabilities or the inherent drawbacks to some of these. So as I've said, once you've picked, I'm a specialist in polymers. I'm going to try and solve the biotribology problem with polymers. There's always something that you're working against. Especially with polymers, they tend to have issues with extrusion. So ultra high molecular weight polymers, PTFE, the reason they're so slippery is because there's very low cohesion between those joints. So you could think of it almost long-term like extrusion of an O-ring. You clamp down a PTFE O-ring, it extrudes out, fills the space, creates a seal. But if in a joint or a hip area under repeated compressions, that polymer can creep or extrude. So my background's in polymers, and it's as much knowing about the limitations of polymers as it is where you would use them. And then metals and ceramics, as I've said before, they're tougher materials, but you're always working against some magic material. And that's kind of really what I wanted to highlight in this section. This high-tech fantasy, 100 years in the future, we're still dealing with the same physics that we have now. So to summarize this section, this is a little bit of a kind of intermission between my next favorite part. I always think of things as a material scientist. It's kind of what I've evolved into over time is the processing. So like that roughness, what surface roughness do you get from these different materials? The structure, so what kind of, how does the cleaning, the polishing of these different materials that you've chosen through the tribology, how does that affect things like the lambda, the lubrication regime, and then how does it affect downstream issues, complexities, repeated impact? Are you using it in somewhere that takes on a lot of load, like a hip or a knee, or something like an elbow? So it's very contextual. There's no magic material. So something to think about in your material selection. Okay, and then the last section is forged in fire. So this has been a real big passion project for me. I'm going to talk a bit about specifically one area of research that I've really ridden one of my lab people over, but he's done I think a fantastic job. So we're going to talk about Forged in Fire. This is a really popular show. Essentially think of it as Chopped or Great British Baking Show for historical and cultural weapons. So people go, I want to, to demonstrate the competitive skill of these bladesmiths, they're going to remake a saber or a war axe or something. And they have to go and take an ingot of material, hammer it out, to bright glowing red, they hammer it, they treat it, and then they do things like quenching, tempering, all these metal transformations. What I find is a good opportunity to talk about is quench oils. So quenching the sword or the spear or whatever they're making is always this big dramatic moment in the show. So, if you like big dramatic moments like this and you want to turn that into career, something like quench oils could be a good gateway. So I'm going to talk a bit about formulating. And then because we're talking about lubricants that are supposed to catch on fire or, going to be in high temperature areas, I'm going to use the last bit of this talk to talk about fire resistant lubricants and how do we engineer for some more safety. And maybe if your mechanical system that you're developing is in proximity to fire or open flame or high arcs, that maybe you want to go away from petroleum or hydrocarbons to something a little more safe. So kind of a big cut. So quenching, this big dramatic moment, they take this glowing red sword and then they plunge it into a drum full of some fluid and it hisses and steams, and they give it a lot of attention on the show. The purpose of quenching is you've got this superheated piece of metal. It has a lot of degrees of freedom, and depending on how quickly you cool down, let's say that steel structure, it will go from this kind of body-centered cubic austenite formation to ferrite, where it kicks out some of the precipitated carbon, or it'll go to martensite, which is this kind of elongated, more tensile strength material. So depending on the purpose of the forged item, it could be one of these weapons they're making. It could be rebar, part of a drivetrain. how quickly you quench that hot piece of metal determines whether you get the sparite structure, which is very hard, has good work, good sharpening ability, a good ability to take an edge. Versus rapid cooling, you get something with greater tensile strength. So how quickly you're able to achieve that cooling affects the final properties of the material, even though it's the same number of atoms with the same stoichiometry of carbon and steel or carbon and iron. It's different. So it is a big job. It's done on, you know, claymores and swords and all sorts, but it's also done on giant industrial scale as well. So we want to make sure that we preserve the integrity of the materials and that we quench slow enough or fast enough to meet the desired tensile strength and hardness of that material. There's a lot of options out there. There's water-based or oil-based. We focus primarily on oil-based just because it's kind of a new area for us, these quench oils. We're offering quench oil packages. And water-based is probably the next phase for us. It just has some of its own complexities. Okay, so quench oil. The way you can measure quench oil performance, there's two main tests. There's the GM quenchometer test. This is a really cool test where you heat a nickel ball up to about 850 degrees Celsius and then drop it into your quench oil. The interesting thing about nickel is when it gets to about, I think about 600 degrees, it becomes magnetic again. So you go above the Curie point, the nickel ball cannot be magnetized or has no magnetic attraction. You almost use the magnetism of this ball as a thermocouple or a probe. So once it reaches 600 degrees Celsius or below the Curie point, it swings over and hits a magnet and makes a clink, and then you can measure your temperature or how quickly it went from 850 Celsius to 600. And that gives you a basic cooling rate. You can stack that up against how fast or slow do you want to quench your workpiece. Then you can go to quenchalizer. It takes more sample, it's a little more expensive, but this can actually get you instantaneous cooling rates at specific temperatures as well. So if you're a metallurgist, there's a lot more to talk about. But we also look at coking, oxidation, and surface finish. So when you retrieve this piece of metal, you don't want it to be covered in charcoal or burnt up or rusted. We want to make sure that we preserve this metal, even though it's gone through about 1,000 degrees of temperature change. Something that we look at on the surface level, the surface science, is you have to think of the thermal conductivity. So if you think initially it's very easy, you just stick this hot piece of metal into oil or water, and then it just gives off all this heat. But there's a lot of surface chemistry involved. So if we've got this hot metal surface and the quench oil is kind of stealing the heat away, what's going to happen is that quench oil is going to pyrolyze. It's going to turn on into carbon deposits, and those can be insulating. We can have the petroleum oil spontaneously flash vaporize, and it's forming a gas or vapor barrier. And then we can have inorganic components of the quench oil decompose into oxides, which tends to be most favorable. So the level of atoms we put into the quench oil generates three different kind of regimes of surfaces. We've got a carbon layer or a char layer, which could be very dense and actually thermally conductive, or it could be quite insulating, almost like an aerogel. The vapor is quite unfavorable. So what we want is sort of an oxide layer. We have certain inorganic metal species in the quench oil, and they decompose into, rather than this carbon, a very dense, nice oxide layer that transfers heat, not as rapidly as the metal, but much faster than a carbon aerogel or a vapor barrier layer. So we can control that with things like detergents, surface active materials. And then we also want to make sure that we have good oxidative stability, so we can do the whole process all over again. Last piece is fire-resistant hydraulic fluids or fire-resistant industrial fluids as well. So the whole COVID era was marked by a lot of thermal events, as my plant manager calls it. You don't say the F word. It's like saying Macbeth on the stage. But hydraulic systems, they do two things. They transmit power. You can use them in power hammers to forge giant axles or propellers for boat shafts and things. The second thing they do is leak. So hydraulic systems, the elastomer is going to fail, a seal is going to fail. Someone might run over it with a forklift, and it's going to spray. And if that spray hits something like a ignition source, it's going to turn into a flamethrower. So it's a big problem, especially if I've got this great big love of quench oils. I don't want to cause all sorts of thermal events. One of the big things with Factory Mutual is this is a program that certifies the inflammability of lubricants in industrial settings. So you want to make sure your warehouse is properly insured. The lubricants that drive your equipment, especially in boundaries and things, they have to be Factory Mutual assured. Nice thing to note is if you're going to get a Factory Mutual approval, if you're a blender, you should probably, I think it's in good form to inform your additive supplier as well. Because once you've approved a formula, it's locked in. They will watch you make a batch. They will like seal it up, take it to the Factory Mutual test lab and test it. The 4 parameters they test for are heat of combustion, the density, the critical heat flux, which is kind of it's essentially the transition between gas to, or liquid to gas. So how, does it evaporate faster than it vaporizes, kind of. And mass flow, so misting capability. And then they generate this SFP number. If you're above 5 to 10 to the 4th, you fail. If you're below 5 to 10 to the 4th, you pass. Your ability to form a flame that will be sustained by a spraying leak is minimal. So you're safe. There's a lot of ways to beat the test. Typically, you're looking at higher flash points, more importantly, higher fire points. So at what temperature does that base fluid catch on fire? I tend to say base fluid because we've maybe gone from petroleum to synthetic esters, to PAGs. You can also lower the misting by adding things like polymers, viscosity modifiers, anti-misting agents. Here's some real basic spray testing we did with 0.01% of the polymer. It changes completely the spray pattern from a spray, high surface area, high combustibility, to a jet. And then the last piece is self-extinguishing thermodynamics, so phosphate esters. I'm not a big fan of them, but the energy it takes to combust the phosphate ester, and it consumes essentially more energy than it takes to burn. Rather than you burn a candle, it puts out more energy and it kind of sustains itself. Phosphate esters almost have like a negative enthalpy of combustion, so they are self-extinguishing. So to show you some chemical structures, most popular is water glycol. You're typically, if you use 60% water, you might automatically pass, but there's a lot of issues with having water. You've got to worry about the effects of microbes and things. That's become a big workplace issue, is the people being exposed to microbes growing in the water. You can use polyol esters, even vegetable oils, polyalkylene glycols, or as I said, phosphate esters. These all have better cohesion, lower volatility, higher fire points, and they have tended to be safer, less liable to work around. So you want to make sure if you're speccing out a lubricant, there's a company I'm pretty close with where they had this big piece of equipment in a foundry, and the OEM for this, let's say it's like a power hammer. So it's just a big hammer that it rounds out a giant square ingot into a drive shaft for a big piece of equipment. It was a European OEM that made the power hammer, and they only spec'd in mineral oil. They wouldn't warranty or do anything with this piece of equipment if they changed it to a proper fire-resistant hydraulic fluid. And I said, you guys got to change this. I mean, you got to like strong arm this OEM, the equipment manufacturer. And what happened is hydraulic fluid sprung a leak, shot into an ignition source, and it burned down the factory that was like the core of this whole business, is this giant metalworking facility. So, that's kind of part of the education that proper lubrication recommendations have to factor in. So origin boundary lubricants, very high intensity, a lot of dramatic elements to it. So if you host a blacksmithing session and then show people there's a lot to lubrication, especially at these extreme ends, this forged fire show has kind of become like a real cult phenomenon. And be safe. You can design safety into not just your safety factors of your mechanical systems, but also safety factors into your lubricants. So it's a big field. I've covered a lot. In grad school, I was kind of the short order cook, the guy who went and did all the different little projects, and it's kind of I like to cover a lot of things, maybe at a pretty thin level, but it's a big field. There's a lot to talk about, and everyone you meet's doing something different. And a lot of people I've heard a talk to in the industry at ILMA, SDLE, never even thought about this. This little piece of equipment, this assembly system needs a special loop. So there's a lot of depth. So pop culture tribology. How do you get younger people excited? You know, people don't change their oil anymore. We've become kind of distanced from oil maintenance as you used to grease your car, you used to change your oil, you make your kids do that. And now you just go to a Jiffy Lube or something. And so we've kind of distanced ourselves away from getting your hands dirty. So we move away from, you know, hands to eyes, we get people's attention, get associated with these big cultural phenomenon that are going on. How does tribology fit into what makes those media work? How does tribology and our sense of just tactile feel, our notion of physics and all of that, how does that mesh with what we see on the big screen when we say that's a good stunt, that stunt made a lot of sense, versus, oh, that was a pretty corny stunt. So it's a big industry. And thank you. I mean, this is a bit more experimental than I usually do. It's typically take a more technical commercial flair, but again, thank you for being let me share some ideas and some experience.